Hello everyone. Thanks for attending my session. I'm Jinwoo Kim from Georgia Institute of Technology. Today I'm going to present PPA and reliability trade-offs in heterogeneous 2.5D ICs using different interposer technologies. Interposer-based 2.5D integration provides the reuse of existing IPs, enables a heterogeneous integration, and significantly reduces design time and complexity by reutilizing chiplets as plug-and-play models. The recent Intel's Foveros and AMD's Zen 2 architecture indicate that 2.5D technology is no longer an alternative to the traditional 2D SoC, but a new trend. In interposer-based 2.5D technology, silicon, organic material, and glass are commonly used for an interposer due to their characteristic. The silicon interposer has good performance and routing density, but the cost is higher than other interposers. In case of the organic interposer, it has low fabrication cost while it shows poor performance. The glass interposer has low cost and reasonable performance, but it is difficult to process and has poor thermal conductivity. Therefore, the overall performance, reliability, and design cost of 2.5D IC depend on the interposer technology. In this work, we design large-scale heterogeneous 2.5D ICs using silicon and LCP interposers. We also perform PPA analysis, signal integrity, power integrity, and manufacturing cost analysis on those designs. Finally, for the first time as far as we know, we observe quantitative trade-offs in terms of PPA, SI, PI, and fabrication cost depending on interposer technologies. The left figure shows our 2.5D IC design and analysis flow using commercial and in-house tools. From interposer and chiplet PDKs, chiplet-to-chiplet protocol, and netlist, our tool first generates interposer and chiplet designs. As the interposer wires are large unlike on-chip wires, the I/O driver optimization step is taken before chiplet design stage for proper signal transmission. In I/O driver optimization, we generate multiple sizes of Intel's AIBs according to the wire length distribution of interposer. First, we implement the target interposer wire lengths as SPICE subcircuit by cascading TX line models from HFSS. Then, we perform the simulation over the wide search space of TX RX sizes and select the combination with the minimum propagation delay. Verilog netlist with selected TX RX sizes is generated and delivered for the chiplet design stage. Finally, we perform various analyses including PPA, SI, and PI for the design validation. In this work, we designed two 2.5D ICs based on silicon and LCP interposers. We choose silicon interposer technology based on TSMC CoWoS and LCP interposer based on Panasonic RF705S. When compared to silicon, LCP has one additional metal layer and larger physical dimensions in metal line pitch, micro bump pitch, and C4 bump pitch. In chiplet design, we choose a regular bump assignment, which is placing signal bumps in the center and power bumps at periphery to ease the IP reuse. Moreover, to minimize the wire lengths of chiplet-to-chiplet connections, we adapted area I/O placement to let I/O drivers be placed near their micro bumps. All chiplets are targeting the operating frequency of 1 GHz. Logic chiplets are designed with commercial 28nm technology, and IVR chiplet is designed with 130nm technology to take advantage of heterogeneity of 2.5D. In LCP design, the footprint of each chiplet has increased because of 3.75 times larger micro bump pitch than silicon design. In case of NOC and memory controller chiplets, the area of micro bump array dominates the logic area, so the chiplet areas have increased by 14.06 times. Because of the longer wire lengths in LCP chiplets, the switching power of each chiplet has increased up to 30.4%, which leads to the total power increase. For effective power delivery, top two metal layers are used for PDN in all chiplet designs with 20% of maximum occupancy. All chiplets satisfy the worst IL drop less than 5% of supply voltage. In interposer design stage, we place all chiplets and passive components on the top side and all C4 bumps at the bottom side. For the passive components for IVR, we choose the solenoidal embedded inductor and low-profile capacitor. Before the signal routing, we place the mesh type PDN on the lower two metal layers. Total 1,420 nets are routed through the interposer layers in all designs, and LCP interposer used one more metal layer than silicon interposer for the routing resource. As design rules in LCP's interposer are larger than silicon, LCP interposer has 4 times larger area and 1.8 times larger maximum wire length than silicon interposer. In this slide, I will present how we analyze 2.5D ICs. For timing and power analysis, we first generate transmission line models in the interposer design. We design the unit cell model with PDM mesh using HFSS and cascade them to generate full transmission line model. We run SPICE simulation with the following test bench for the analysis of transmission lines. Timing and power analysis results of chiplets are directly obtained from Synopsys prime time. For signal integrity, we first choose the complex channel model from our interposer design as shown in the figure. The channel model is then divided into 5 segments, and all are characterized to S-parameter models. We import segment models into Keysight ADS and run simulation with the data rate of 1 Gbps and the crosstalk model at each input of aggressor. For power integrity, we perform frequency domain and time domain analysis. To model our mesh type interposer PDN, we choose transmission matrix method to divide interposer PDN into n by n unit cells as shown in the figure. Each unit cell is modeled as a lumped pi model with frequency-dependent RLGC elements. By cascading those unit cell models, we analyze interposer PDN impedance and the transient characteristic of power delivery, including IVR chiplet. All analysis results will be discussed in the next slide. The table on the right side shows the overall comparison between silicon and LCP designs. As I mentioned in the previous slides, LCP interposer shows 4 times larger area and 1.76 times longer average wire lengths than silicon interposer because of its larger physical dimensions. Since LCP design has longer interposer wires, I/O power in LCP design is 1.33 times higher than silicon design, which mainly leads 1.1 times higher in total power. In signal integrity, LCP design shows 21.94% smaller eye height than silicon. This smaller eye height comes from intersymbol interference because of the impedance mismatch at the receiver side in LCP design. Because of 0.02 times smaller resistance in LCP transmission line, the reflected signal distorts other signals in the victim line. In terms of interposer PDN impedance, LCP design shows 0.95 times smaller DC impedance and 2.34 times better bandwidth approximately. For power integrity in time domain, LCP design has 1.62 times higher initial ringing and 1.33 times larger output ripple than silicon, whereas others remain similar. Higher ringing and ripple come from smaller inductance and capacitance in LCP design due to its lower dielectric constant and higher dielectric thickness. These overall comparisons between silicon and LCP designs show the trade-offs in terms of PPA, signal integrity, and power integrity depending on interposer technologies. In this slide, we perform the cost analysis on two 2.5D designs. The total cost of 2.5D design can be divided into interposer, chiplet, and bonding cost for simplicity. We estimate the overall manufacturing cost using parameters in the left table. From our estimation, the total cost of LCP design is 2.69 times higher than silicon design as shown in the right figure. Even though the interposer cost was 1.91 times less, the chiplet cost was 4.2 times higher because of larger area of chiplets in LCP design. We also performed the cost estimation of LCP design assuming interposer technology improvement same as silicon interposer. In predicted estimation, the interposer and chiplet costs have reduced to a quarter approximately. This predicted result indicates that the dimension improvement of LCP interposer is necessary to maximize its low-cost benefit. To summarize our work, we conducted quantitative comparison in terms of PPA, reliability, and cost between silicon and LCP interposer-based 2.5D ICs using commercial quality design and simulations. We developed PD analysis framework which integrates frequency domain models into time domain simulations. Our work observed a wide range of trade-offs between two 2.5D designs in all aspects. Thank you.